All right, so the next session will be presented by me, Francois Labuschagne. I'm part of the Core Deep Learning team at ASIC Design Services. And we'll be focusing on how to implement a simple person presence detection CNN on the SMF2000 board. So firstly, we'll just have a quick look at what's available on our demo platform before discussing what is needed from the Core Deep Learning side to go into the FPGA flow. At that point, we'll start our first hands-on portion where we will be using Libero to create the FPGA design, and we'll let that run in the background while we discuss the software running on the Cortex M3 and the general data flow through this system. Thereafter, we'll have a hands-on exercise with Soft Console where we will be compiling the software that manages the communication between the PC and the demo running on the SMF2000. And then finally, we'll discuss the ins and outs of the PC side software, which is included in the archive I've sent to you. Right, so our demo platform, for those of you who are not familiar with this, it's the SMF2000 board. It's a very low cost development platform showcasing this Microsemi Smart Fusion 2 SoC, in particular the M2S010. This is on the smallest scale of FPGAs offered within that family. It's only got 10,000 registers. On this board as well, what we'll be using is 8 megabytes of SDR SDRAM. There's a 25 megahertz crystal clock source on the board. There's a UART over USB, which we'll be using to transfer data from our webcam on the PC side to the board for processing, and we'll also retrieve the results via this link. And then we've got some user LEDs to showcase our results. So the Smart Fusion 2 SoC, that'll be used for our deep learning engine, or the FPGA portion. The Cortex M3 will be running our communication link between the PC through the UART, as well as doing the final post-processing of the CNN and displaying our results. The 8 megabytes of SDR RAM on board will be used for storage of the weights, the activations, our input images, and the results from the network. The 25 megahertz clock source will be used to drive our Cortex M3 processor at 96 megahertz. This can go up on this board to 142 megahertz, but we've chosen this frequency to maximize our baud rate through the USB UART. And we're also generating 104 megahertz for the FPGA clock and our SDRAM interface. The UART itself, it's configured for 6 megabaud over this USB link. And then finally, our 9 user LEDs will be used for our results encoding. So the 8 LEDs that form part of the row on the side of the board will be used as a bar graph to indicate the probability of the detection. And on the other side of the board, there's a single LED that will just indicate the activity as the network is running. So this is the overview of the data flow and the operation of the demo we'll be presenting. So for this demo, you'll have the SMF2000 as well as a PC with a webcam and JPEG images. So once we start up the demo, the PC will initialize the UART link and establish communication with the Smart Fusion 2 SoC, and then load the CNN weights over this UART link through the SoC into the external memory. Once that is done, the operational loop of the demo basically entails capturing an image from the webcam, loading that image data into the CDL memory space inside the external SDRAM. Once the engine is idle, it will start execution of that memory space, wait till it's done, and then read the results back from the memory space for the post-processing. The whole system comprises of 2 memory spaces, so we are able to upload one image to a memory space 0 while we're executing on 1, or upload to 1 while we're executing on 0, so to keep the engine fully occupied. Right, so moving on to the FPGA flow. For implementing the CDL processing engine inside the FPGA, there's 3 major inputs that we require from the compression and design space exploration phases, which Hardest showed earlier. The first is the memory file. So this is the quantized network weights that the network will use during the processing. It also includes the BIOS information. The second is the system Verilog core parameters. So this describes this particular network accelerator that you've developed using the design space exploration phase, given the constraints placed on the system, the amount of memory bandwidth, the DSP blocks you want to use. All of this is encoded into this Verilog parameters that then is used to initialize the Verilog core that will do the acceleration. And then the final input is the memory map that will be used for this network. So the important memory addresses are firstly the weights. So for normal and the standard flow, our weights always sits at an offset of 0. The heap is where basically scratchpad memory for execution, and then you've got your input address and the output address of the CNN results. We also provide you with an offset that will specify the amount of bytes offset in memory into the second memory space for your dual buffer system. So firstly, I would like to give you an overview of our most basic interface to the IP. We've got 3 clock and resets domains on a typical application. The first will be the AXI clock interface, which is used for your external memory bus. We've got an FPGA clock domain, which is the main processing engine, and then an APB interface that gets used to set basic registers, control the core, some runtime statistics, monitor execution, those sort of things. And then we've got an interrupt indicating whether this is done, and there your AXI master interface that goes onto the main system memory bus for accessing your DDR or external memory. Moving on to the SMF2000 board, we've got a couple of modifications to the standard interface to support this platform. So firstly, the biggest difference between the SMF2000 and any other board we will be using is it does not have a DDR memory on board. It's using single data rate SDRAM attached to normal FPGA I/O. So in a typical system, we would be able to access the DDR on the Smart Fusion 2 via the MSS AXI bridge, which is not possible on this board due to the SDR memory sitting on FPGA I/O. So what we've done is we've changed our standard AXI master interface to support direct SDR interface. So Microsemi provides core SDR for interfacing to this SDRAM, and we've modified our implementation to directly connect to this. This M2S010 is on the scale of devices we support. This is on the very low end, the smallest ones that we can run a CNN on. So in order to save logic, we couldn't add AXI interconnects into this design to support sort of a standard AXI bus. So what we've done is we've got an internal memory port through the IP to access the external SDRAM, which I'll show you later on. Some other optimizations we've done is we've removed all the core statistics, so the execution times for layers, those sort of things, and we've gone for a very basic GPIO control interface. So you will see that there's only a couple of IO pins we use to toggle this core. It's the start, stop, memory space, those sort of things. So this is what we will be using today. So firstly, you'll see we've got two clock and reset domains. The FPGA clock is used for the deep learning engine as well as the SDRAM controller. We've got a memory clock, which is the APB memory interface to the Cortex M3 system. On the control side, we've got three GPIOs. So a single bit for starting the network. So then if the core detects a rising edge on this signal, it will start execution. We've got a memory space select line for switching between memory space 0 and 1. And we've got an interrupt line indicating when the execution is done. Our APB memory interface used for the external SDRAM access is mapped into the Cortex M3 memory space, as you'll see later on. Then additionally, we've got some flow control signals for enabling our peripheral DMA controller in the Cortex M3 subsystem to efficiently transfer data through this APB interface. And then you've got your SDRAM interface to connect to the IP that will manage the memory controller itself. All right, so next on, we'll move on to Libero. So for those of you that do not have Libero installed, I will run through this exercise with you so that you can see the steps involved. So the way that we will be conducting this exercise today is through a three-step Libero scripted approach. So I provided you 3 scripts labeled 1_, 2_, 3_ for the various steps that we want to execute. So in the first part, what we will be doing is we'll just make sure that everyone's got all the needed Libero IPs. In this very simplistic design, we're only using 3 of them, which is the fabric clock conditioning circuit, the core SDR for the memory interface, and then the IP block for the Smart Fusion microcontroller subsystem. In addition to downloading these IPs, this will create the Libero project for you. It will import all the needed Verilog files and create the APB core wrapper around core deep learning, and then generate all the Libero IP blocks needed for the design. So the way that you will be able to execute these scripts is from Libero, either by using the shortcut key Control-U or going to Project Execute Script. It will bring up this dialog box, which will allow you to specify which script you'd like to execute. So let's try the first one. I'll jump to Libero quickly. And then from there, I'll map my first script. So like I said, either project execute script, or you can say Control-U to do the execution. You specify the path to where that script file is located. So let's run this. So settle, I've created a new Libero project for you. It selected the appropriate Smart Fusion 2 parts with the appropriate package and temperature ranges, speed grades, and so forth. So once this is done, you'll get a report about the script execution. You can just close that. Then if you look at the design hierarchy, you should see something very similar to this. So firstly, we've got a Verilog file for SDR data control. This file manages the data masking and the data bus of the SDR memory. We've got a reset controller and synchronizer. We've got two phase lock loops or clock conditioning circuits, one for generating our Cortex M3 operating frequency and the other one for the FPGA frequency. You've got your memory controller, Core SDR. You've got our IP, Core Deep Learning version 1.3. And you also got a smart design canvas where we'll start instantiating our various components, including the SmartFusion 2 MSS. All of these have been pre-configured with the scripting interface, so you don't need to go into these settings. We'll just start using them in the next phase. So the second script, which is called to_build smart design, what this will do, it will firstly instantiate all the IPs in smart design. So as you can see on the bottom left, this is what the instantiation will look like. You've got the memory controller, our core deep learning, the SDR data control, and the SmartFusion 2 MSS. Then we configure all the constant pins for the SDRAM controller. So these are memory timings, cache latencies, those sort of things. It'll create all the connections between these components, create the top level ports for the design, and also set up all design constraints, including I/O and timing. So if you jump back to Libero, we go through the same process again. Control U or project execute script, and then you specify this particular script that you'd like to execute, or to_build smartdesign.tcl. And as you see, as it runs, it should populate the smart design canvas and start connecting everything together. Once the connections are done, it'll jump to your constraint manager and specify your I/O constraints. So you'll see in I/O attributes, there should be one file selected for place and route, and timing, we've got two separate timing constraint files. If you look at the smart design that's been created, you can see there's core deep learning. We've got our SDRAM signals running to our core SDR and to the data control portion. We've got our memory bus, APB memory mapping to the SmartFusion 2 MSS. There's our UART we'll use to communicate to the PC. And then there is GPIOs to control the core. So 0 to 8, these are all our LED signals used for activity indication. Then you've got GPIO 16, which is the start network. 17 is memory space selection. 18 is an input that's an interrupt for the network done. 19 is a time bomb indicator. So this design will run for 10 minutes before the time bomb fires, and the outputs will be 0. So that just gives us an indication that has happened. And then pin 31, we just use as a FPGA reset for the system. All right, so going back to the slides. The final step of the FPGA design is to actually run the tool flow. So we provide you with two options today. You can either run the tool flow, including programming the Cortex M3 embedded non-volatile flash memory. So the actual software that runs on top of the Cortex M3, that will be programmed with the first script. And if you're going to step through the soft console demo later on, you can use the no flash version, which will blank the flash memory of the Cortex for us to load the software in through the debug interface as a final step later on. Right, so I'm gonna run the no flash script so that we can program the flash using the soft console debugger. Again, Control U, which will bring up the execute script, and this will run firstly synthesis, then it will do a single pass, place and route, verify the timing, and then program the FPGA for us. So I'm just going to hit run, and this process will get started. So depending on your machine, this will take something between 8 and 15 minutes for all the processes to complete. So while we let this run in the background, I'm going to go back to the slides and we'll discuss some of the other data flow within the system. All right, so just while we run the FPGA, just a note on the scalability, and you should have seen this slide already during Hardis's presentation. So today we are using an M2S010. So we're sitting right at the bottom left-hand corner of what is possible with the microsemi FPGAs. And this same network we developed today, we can scale that up to any different FPGA size in the family. And the only thing that will be different between them is the performance. So the frames per second that we'll be able to achieve on these platforms. There won't be any difference in terms of the results or the accuracy. The only thing that scales between the families is the performance level. So to give you an indication of what we're doing today and comparing that to some other networks that we've implemented to give you a good feeling of where we're sitting at, what performance levels are possible. This network for person presence detection we're using today is based around SqueezeNet. It'll be running at 140 megahertz. It's a very small network, keeping in mind that this platform is very constrained in terms of the amount of computational resources available. So our IP on this one will be using around 8K LUTs and registers, and we're using pretty much all of the embedded RAM blocks within the device. For the actual execution, we're using 12 math blocks or DSP blocks. We use this in a very special way, which is known as the dot product mode. And this is available on all the Smart Fusion 2 and PolarFi FPGAs. And basically what this allows us to do is to do two 8-bit multiplication plus an addition in a single 8-bit and a single multiplier block, effectively doubling the performance we can achieve on a given platform. And this is also why 8-bit quantization works very well for FPGA families, is we can use these special modes inside the DSP blocks to greatly enhance the performance that we are able to achieve. So this demo today, if you run it full throttle, you'll be able to do 9 frames per second. And the power consumption is 465 milliwatts for the total SoC device. So as I've just mentioned, with these flash-based FPGAs, we play in a completely different power domain than you'll find with GPUs or other SRAM-based FPGAs. So you've got a full neural network inferencing engine running sub half a watt on an FPGA. That gives us a total performance per second of 3.4 gigaops per second. Keep in mind, we're only using 12 DSP blocks for this, which gives us a power efficiency ratio of 7.4 gigaops per second per watt, which in the larger picture of the microsemi FPGA ranges is actually sort of on the lower end compared to what's achievable. To give you a more feeling of what we can do on PolarFi devices, when we move to them, suddenly we've got a considerable amount more processing resources available to us. And now we can clearly see what Hardis showed earlier in those graphs about designing a network for performance versus efficiency. and the differences we can get with that. So we've got the exact same network, TinyYOLO version 2, running on the same FPGA, the MPF300. It's the 300,000 LUT FPGA. We run that at 200 megahertz. A single frame is 5.5 gigaops per second. On the one hand, we aimed for efficiency. So we're only using 35K LUTs, 50K registers, whereas for performance, we pushed that up to 70K and 92K. So the main difference you'll be able to see here in the math block summary, 256 compared to 704 for the processing. Now the performance between the two is considerably different, nearly double, but you can see in terms of our power numbers, we can do on the one platform, the full FPGA power, including DDR controllers, is at 1.7 watt compared to 4.3 watt for the high performance solution. So even within a single device, we can scale the solution to either fit your performance or power budgets for your specific project. And then you can see the final numbers. The ones that are actually making, we need to look at is the power efficiency, the gigaops per second per watt. So on the one hand, we execute nearly 84 gigaops per second per watt compared to 76 on the performance model. Just a note about these gigaops per second. These numbers aren't the theoretical numbers calculated from the operating frequencies. These are actual computed operations. So to get these, you take your network gigaops and you multiply that by your frame rate to get these numbers that we've listed. So these aren't marketing numbers. These are actually computed giga operations per second on these platforms. Let's just have a quick look back into Libro where we see, okay, we're at place and route now. So it's progressing very nicely. Okay, so the next section of my presentation is discussing the SDR, SDRAM access and the data flow through our demo. So what we have is a system based around various DMA channels within the MSS to move all the various bits of data around, and then some status LEDs to show the result. So there are four main DMA channels in the MSS that we've set up. So a peripheral DMA channel in SmartFusion 2 allows for flow controlled data to various peripherals. So to make sure we don't overflow or underflow any of the FIFO memories. So the four important ones we use today, we've got one DMA channel receiving our UART command block, which will save that into internal Cortex M3 SRAM. So this basically gets them decoded to understand what type of UART command we'll be executing. This can either be a read of the CNN results back to the PC, which will trigger DMA channel 0, the Cortex M3 SRAM to transmit channel of the UART. We've got the UART receive to SDRAM, so taking our image data from the UART and pushing that into the SDRAM. Then SDRAM to Cortex M3 SRAM, which is the results that we retrieve from the FPGA and save that into the Cortex M3 SRAM. Our GPIO channel mappings, 0 to 7, is a bar graph of this calculated CNN result. So it's encoded probability that there's an actual person within the image that we've received. Channel 8 is just activity, so memory space. 16 and 17 is our control for starting the network and selecting the memory space. 18 is our interrupt. 19 our time bomb indicator, and 31 our reset. So this is an overview of the SmartFusion 2 SoC. So if you look at this, what we'll be using today, firstly, there is our UART. So we'll get data in from there through the APB, through the AHB bus matrix, either to the FPGA or to the internal SRAM. So the way things will work, is the first step will be data coming in from our UART. The DMA will move that directly into ESRAM, where the CPU will calculate or determine what type of operation we will be doing. The second channel is from the UART through the fabric interface controller into the FPGA and out through FPGA I/O into the SDRAM. Then we've got a channel running from the FPGA back into processor memory for storing of the CNN results. And then finally, we've got a channel for loading or sending back the CNN results from the embedded SRAM back out the UART. So as I mentioned, we've got a bit of a unique setup for accessing the SDRAM through the CDL engine, as we can't instantiate a full AXI interconnect. So we've got a very basic FIFO interface mapped into processor memory. It basically uses 4 addresses. We've got a data register for reading and writing data to this memory, a control register for the size of the transfer, the address of the transfer, and a control register which says whether it's a read or a write operation. And we map that to the specific fabric interface controller which sits at this memory location. So you'll see from the software that I gave you, this is the basic procedure of reading and writing to the SDRAM. You set up the transfer size, the address, and you say we're writing, and then you can start your DMA controller to transfer the data from the UART to the data register, and the reverse for read operation. We set the size, the output address, and we read back, start the read operation and activate the DMA channel. Right, so next step is our soft console hands-on exercise. So let's have a quick look at where Libero is now. So mine's busy verify timing, so it's only going to be a couple of more minutes till the FPGA is programmed. So it's an appropriate time to start soft console. All right, so for soft console, there's a couple of things that we'll need to configure. This is just mainly to show you what the procedure is. There's not a lot of work involved. It's going to be commenting and including some code to make this work. But basically, we need to configure the software in the Cortex for the appropriate memory areas and output sizes and so forth. So firstly, we'll define the output address of the CNN results. We define the output size, as well as the buffer offset for our double memory space. We'll implement the post-processing. So for this particular CNN, we've got average pooling and a softmax post-processing. Just a note, we can implement the average pooling layer as a fully hardware accelerated layer. In this example, it's a very basic pooling or a very small amount of data that needs to be processed, and the trade-off between keeping it in software and putting it in the hardware in terms of the size of the core just made more sense to implement it on the software side. So that's why we've got that there, but that can easily be moved into the FPGA fabric as well. And then we're finally just doing a softmax to calculate the probability of the actual detection. All right, so setting up soft console. So firstly, I did provide you in the archive, there is a folder called soft console _6p2, which is and that folder contains the software project which we will be using today. After we've pointed soft console into that space, we'll need to import the project. So what we'll do is we'll select import projects. We'll go to existing projects into workspace and then select the root directory of where our workspace is located, and making sure that we've selected this particular software project. So let's quickly go through that. So let's just jump back to Soft Console. You can see my Libero has actually completed while we were away, and it would have programmed the FPGA as well. So it's pointing Soft Console to my project directory. You can just say launch. Once you've got the Soft Console interface open, you can just say import projects, general, existing project into workspace. You select the root directory. So normally you can just hit browse and immediately press enter because it'll be in the appropriate directory. You'll see the software project popping up and you can just select that to complete the import. Right. So most of the work's been done for you. If you can do a Control B for building the project, it will fail at this stage as we haven't defined all the various bits and pieces for this network. So the first thing you'll see it'll complain about is in our main file, there's a section where we use the output address and the buffer offsets for this particular network. So these are all defined within the following files. It's called cdl_ppd_interface.h. And that's where we define our network output address, our buffer offset, and the size of this particular output for the CNN. So you can see 270 bytes. Then we do as well in the CDL ppd interface.c, there's a post-process function where we'll be doing our average pooling and the softmax function. So let's jump back to Soft Console. So this is not going to be a lot of work. It's merely to illustrate what setup needs to be done. You can have a look through the various codes to see how we interact with the core as well. So you can see we've got functions to start the core, clear the interrupt, set the memory space, but these are basic toggling of GPIO, so it's not a lot to see there. So you can see at the top, this is where we define our output address, so we can just include this so to specify the output address, the offset, and the output size. And when I go through this, the PC side of things, you'll see these addresses again, where we configure our PC application. And then we need to do our post-processing function as well. So in the code, you'll see two sections, the average pooling and the optimized two-class softmax. At this point, this entire software project will run and the PC demo will work. We'll need to include this if you want to show the bar graph on the LED. So we're doing basically the post-processing twice, once on the Cortex M3 to show the bar graph on the LEDs, and then a second time on the PC when we calculate it for our demo GUI. So once you've included that, your project should compile, and we are ready to basically download that into the Cortex memory space. So just to show you how we'll set up the debug interface, if you're not familiar with Soft Console, it's going to be an entire session on its own. But the basic idea, what we'll be doing is after we've built the project, either Control B or build project build all, we'll load the executable through the debugger. So we'll go to run debug configurations. You'll create a new profile for this instance. And the only setup that you'll need to do is you'll need to copy these two commands, command set device SMF2000 and fileboard microsemi cortex m3.config into your config options. And once that, you can just hit apply and run the debugger and it will load your code. So let's look at that. Back to soft console. Debug configurations, create a new one. And we go to the second tab and we just add these config options. I'll just jump quickly to our Q&A and I'll just make an announcement with these values. You can just copy and paste them instead of having to type them in while I'm jumping around through various sections of the GUI. So you should see them now in the published Q&A. Just apply and we'll run the debugger. Right, so it should start executing, and it'll just stop at a point in your main function, and from there we can now just run the software. Just a note, there's a lot of interrupts running and triggering while this is executing, so if you're going to be stepping through code while the demo is running, the demo PC application will time out, so just let it run or disconnect the debugger and everything will be fine. So before we jump back to this, I'll just discuss the demo application that we've provided. So this is based around something very similar we have for our Ethernet demos for PolarFire, but we just switched out the Ethernet interface for this UART. So when you connect this SMF2000, they will show up two FlashPro 5 COM ports in your device manager. The first one is the programming interface, the actual FlashPro 5, and then the second one is the UART, which you'll be using for this application. We have a setup file to configure this COM port for you. So this is in the demo source files, configurations, demo parameters, ppd 135p.yaml. And this is where you can set up your COM port. You can see the legacy Ethernet code popping up in this. I already sent you the note about the executables. We did see some people having issues where the virus software blocks this due to the files being from unknown origin. I did send you a checksum with the files. They are completely safe. If you want the source code, we will share that with you. It's just because it's proprietary files that the virus software doesn't know where they're actually coming from. We provide you with two scripts, a person presence detection demo.bat, which will run the main demo application, and we've got a test core.bat. This basically tests the core rate that you're actually able to achieve on the board. And in this bat file, you'll need to set up your COM port as well. So this is how the demo will look like. You've got, you'll have two screens similar to this, what you see here. If there's a green box around it, that means there's no person detected. If it's a red box, it did detect a person. And you'll see it might be very faint on these slides, but at the top right-hand corner, when you run the application, you will actually see the probability that's been calculated for that particular image. Just a note on this demo, we are severely performance limited by what is achievable through this UART interface. We're running at 6 megabaud, and we can push that to 600 kilobytes per second of actual transfers. But if you look at our images that we feed this network, they're 270 by 135 by 3 channels for your RGB. It's 170 kilobyte per image. And then we need to add overhead and the readback of results and so forth. So what you end up with is a demo rate of around 4 frames per second you'll see on the PC, even though the core itself is able to achieve 9 frames per second. So when you're using other types of interfaces, we can greatly improve this performance, as I'll show you some of the other platforms we've got available later on. During the demo, spacebar will switch between your webcam and images. and escape will terminate the demo. So at this point, I'm going to turn on my camera, and Andreas, if you can just split the screen so that people can see my board over here. Right, I believe it
you should be able to see your board now.
Thank you. So firstly, I'm going to run this test core file. And basically what that will do is to run the core as fast as possible. So you'll see that various iterations, the first column is the iteration time, and then we just calculate the average time based on all the executions we've done. And this will end up being averaging around 9 frames per second. You might have picked up from some of our discussions that we operate in a batch size of 1, so the latency is equal to the inverse of the frame rate. So this is specifically for low latency applications where low batch sizes are required. All right, and then you can start the demo. So firstly, what you'll see is the uploading of the weights. It will take a couple of seconds due to the limited bandwidth. And then once this is done, it will start the GUI showing you pictures, and then at the top right hand corner, the probability. So you see for high probabilities, all the LEDs will be lit. For lower probabilities, one or none of them will show up. So it really depends on the image that's currently in there and showing you the calculated probability on the PC as well as on the actual device. So you don't need this image, this PC side software to actually run the CNN. This is purely to make the demo more usable and user friendly. All the results can be used and calculated on the device. It's not really needed. There's no post-processing needed externally of the system. Right. Just as a final note on this, as you can see, the post-processing involved is very basic. There's not a lot to do. It can be done on a very simple MCU-based platform like we've seen here today. There's no need for complex operating systems running your full TensorFlow framework alongside the accelerator core. All our processing is contained within this FPGA image, and you just have the very basic probability calculations left as the final post-processing phase of the demo. We've got various other demo platforms available as well. The other demos we've got is person detection. So instead of just saying yes or no, whether there's a person in a picture, we can do the detection with a box. We've got a demo for TinyYOLO V2. We've got a general accelerator demo. And all of these are available on all the standard microchip development kits, as well as the Arrow Everest board. So depending on what device family you're targeting, you can either go for a PolarFire based solution like the Everest board, or their video and imaging kit, or the standard evaluation and splash kits. If you're into space applications, we also have got TinyYOLO running on the RTG4 development board using an Ethernet interface. And then we'll be launching very shortly our Hello FPGA kit demos, where we run TinyYOLO on this M2S010 with a direct camera interface and LCD display of the results. So look out for that. That'll be launching in the next couple of weeks. For now, that is it from my side. Please send us your questions via the Q&A, and I'll be happy to answer them for you.
So Francois, do you want to answer a couple of Questions live?
Yes, I'll have a look. So, see, Pavel asked, he missed how core deep learning was imported into the project. So let's go back to Libero. So core deep learning, if you look at our design hierarchy, it was part of the first script. It's this Verilog file. It's actually two Verilog files. The first one is a wrapper, which just instantiates the encrypted model. And there you've got your encrypted model as a second file. So this is all done in the first script. It's a Verilog file. And all we've done with it is to create the wrapper around it for this APB memory interface. And the rest of the IOs are just general net connections to other parts of the design. Let's have a look. William asked about getting the source code for the demo. Oh, I see Hardis did actually reply on that one. These demos are actually developed in Linux and cross-compiled onto Windows. So the Linux ones are actually a lot easier to use and compile. But we'll get back to you. Just send us an email, either at info@coredeeplearning.ai, or just reply on the reminder email I sent you this morning. And we'll be able to share that with you. There was a question about the soft console project. This soft console project is something that we've created based around some of the standard firmware drivers available in Libero. It is provided in the archive that I provided you with the link on SharePoint before the exercise. So there's a comment about the 12+9 math block utilization. So the 12 is the actual computing DSP math blocks for the CNN acceleration, where 9 is the control circuitry. So calculating offsets and indexing and those sort of things for the core. We do have options to disable those and just implement them in logic, as these are quite small blocks, but for this particular design on the M2S010, it makes more sense consuming that logic into those math blocks. Pressing space gives me an error that the webcam can't be opened. That most likely is that your webcam might be active due to the conference call. That's why I couldn't switch to my webcam for the demo today, so as we are monitoring the board.
There's one more question. What performance could you achieve for person detection on the largest polar fire device?
On the largest polar fire device. So this one particular, we haven't run this resolution on the larger ones. We've run a network with 4 times the resolution on a mid-sized polar fire device. And there it's close to, it's somewhere between 150 and 200 frames per second. So it really starts getting high on those devices. Specifically, this is a very simple network, so the computation is not that intensive. I see, Amish, you've asked about the MCraft Smart Fusion 2 board. Yes, you would be able to port that. You'll just need to take care of the memory interfaces on your own. It would be a bit more difficult as the AXI has been changed, but we can assist you in providing an AXI version. Andy, you're asking about viewing the recording. So I believe that if you use the same link that you've joined with, it will take you to the recording. That join workshop link, we'll keep that active so that it will still redirect to this event so that you can view it later on. Andreas, are there any questions that I've missed, or have I covered most of them? I don't see any more on my side now.
I believe you covered most of them. So maybe let's give it another minute or so and see if there are more questions popping up.
Everyone should have all the demo source now. So even if you didn't have Libero today, or maybe your board got delayed due to various shipping restrictions and what we've got around now, try running the demos later on. Also, if you've got any questions, just email us at info@coredeeplearning.ai, or my main email address, which you would have got in the email from francois.labuskaghni@asic.co.za. You can also reach me on that directly on Teams. So let us know if you've got any additional questions.
All right, I think with that we can close the session. So thank you very much for participating and attending and interacting with us. So the session is recorded, as Francois mentioned, and you should be able to view this session later on under the same link. So thank you very much, and stay safe, stay healthy, and goodbye.